Welcome all of you. So this is the fourth session on the uh, molecular rearrangement and reactive intermediates for the organic synthesis. And this will be a kind of interactive session to solve some of the problems. So you can it will be help you to solve some of the help you to solve assignment questions. Uh, so I hope you are regularly completing your weekly lectures provided on the NPTEL platform. So before going to start the session, I will formally introduce myself. So I am Vijay Rani and I'm a Prime Minister Research Fellow in the IIT Delhi. And today we are here to discuss some of the sample problems. So before going to start some problems, so I would like to take some questions or the doubts from you guys. So uh, regarding if you have any doubts regarding the assignment questions or also regarding the course, so you can ask me. So we'll discuss that one before starting the session. So first, does anyone have any regarding the assignment? So please feel free to ask in between if you have any doubts regarding the assignment question, and we can discuss that one. So you will get the correct answer for your the question. So I will slowly move to the some of the sample problem. So if you have any doubts, you can stop me in between, and we can discuss that one. So here is the first question, and which is based on the radical type of rearrangement reaction. So here you have given one of the starting material. This is the starting material, and in it you can see there are two here C double bond O, OMe. That's the ester group, right? So two ester groups along with the one of the olefin and the bromo olefin, you can say, right? So bromo substitution at its position, and its reaction with the Bu3SnCl. So tributyl tin chloride, 10 mole percent, and the sodium cyanoborohydride, NaBH3CN. So, and among these options, you have given some options as well. So, among this option, you need to find out the correct answer for this. So, in this question, you can see you have the starting in which the two ester group and one vinyl bromide, right? So what happens when this starting material react with the tributyl tin chloride? It gives the uh, radical at this vinylic position. So once this radical is formed, so this radical, uh, what is the how this radical is formed? This tin butyl chloride uh, helps to form the radical in presence of this sodium cyanoborohydride. So this radical forms at the vinylic position. It undergo 1,5 hydrogen atom transfer reaction. So you can see here, if I just label this one, so here this is the one, two, three, fourth, and the fifth position, and the proton transfer takes place. So this is the 1,5 hydrogen atom transfer reaction. So this hydrogen get transferred to the this phenylic position, and the radical is now on the here at the 5 number carbon atom, right? And once this form, it undergo 5 exotropy to get the 5 membered information, because if you look at the ring formation, so 5 exotropy is favored here. It gives the 5 membering with the radical on the primary carbon methyl. So here is the radical. So why this 5 exotropy? Exo means opening of the ring outside. So in this case, if I just show how the endo and exo, I just revise the concept. So in this case, let's see, here is the radical, and the bond formation takes place in this fashion. So here it forms a radical attacks here, and this opens to the carbon atom. So I'll just draw it like the good way, right? So in this case, so this bond pair goes to here, and another bond. So this and the one of the electron. Uh, I just remove the hydrogen, no need to represent this hydrogen, or else I can draw hydrogen in something different way. So here there is bond formation takes place in between. So the new bond is formed in between here, right? So this is mechanism of exo. And why 5? Because the 5 member ring is getting formed, right? So, and what about the when you have the 5 endo? That time, so let's say it is in this fashion. So let's say here is the one radical, sorry, the radical, huh? And now in this case, this is how, let's say bond formation takes place in this manner. So the final product will be this 5 membered ring with the radical here, and this is the newly formed bond is this one, right? So this is newly formed bond. So in this case, this mechanism will be 5 endo. So here in this case, you can see the 5 member ring is formed. It gives the 5 exoteric mechanism. We get the radical at this methyl group, and then in terms of the proton from the solvent, so it gives the final product which has this proton. So this is the newly formed proton which is comes from the solvent. So this is the product is formed after this reaction. So what are the two main steps? So the first step was the uh, radical formation. Second step is the hydrogen atom transfer. So that's also particularly 1,5 hydrogen atom transfer, and the third step is the 5 exo trig mechanism, and fourth step is just like a proton radical abstract proton from the solvent, and proton radical. It gives the the final product. So which is the product here? So this B is the product is getting formed after the completion of this reaction. So this is the it's very simple question based on the radical chemistry again. So any doubt in this question? All right. So we move to the next question. So which is again on the based on the same radical based chemistry. So here what we have given in this question, the major product formed in the following reaction. So we have given one compound which has, you can clearly see there is one chiral center. First thing you need to observe always in the starting material, what are the functional group given in the starting, how the stereochemistry looks like in the starting, and what are the possible active sites to on which this reagent gonna perform the reaction, right? So once you observe all these things, you will get the idea about the initial idea about the what might be the product. So in this case, you can see here there is uh, one ester group, the hydrogen, and here you can see uh, NH and Cl. There is a nitrogen, and if I just draw this in the full manner, just expand the structure. So this is the proton, this is the C O O E T group, and here there is a nitrogen which has the hydrogen and one chlorine, right? So this is the active group in this case. So once this starting material react with the slightly acidic medium in presence of light, it gives the formation of nitrogen radical. So this is the first step you should able to analyze just by observing the structure. So this is the first step or the first step. Now what happens here also you can see there is, so this was the first step which is radical formation on the nitrogen center because this is the most active bond and the radical is formed between, so this bond cleaves homolytically, so HCl get eliminated and it forms the end radical. Once this end radical is formed, so there is you can see if I just label this sequence, so this is one, this is two, this is three, this is four, and this is five. And at this five position, there is a one. You can see there is one proton. So there obviously there are other two protons also. But you can just for our understanding, I will just draw only one proton. Obviously there is two other protons also that I haven't shown. All right, so we have one proton here, and this proton is gonna perform the reaction. So if I just expand this mechanism fully, so if you look at here, this is just elaborated mechanism. So in this case, what happened in presence of proton, it forms such cationic species. Then the light, in presence of light, this bond shows the homolytic cleavage, and the radical is on the nitrogen atom. Now there is, as I have shown earlier, so there is one proton. So this is the proton which undergo 1,5 hydrogen atom transfer again, right? So the same manner, there is one proton and undergo 1,5 hydrogen atom transfer. So the radical form at this position, the 5 number carbon atom right here. And once this radical is formed, so this will be a catalytic, continuous process now. So the this was in earlier the radical formation was up to here was initiation. Now this product is formed in the first step here. This the chlorine propagate this chloride salt uh, and this starting which our the earlier product, so that one earlier radical, so they combine to forms again this active intermediate that I have shown earlier. So this intermediate, right, this intermediate plus this one. Oh, sorry, I haven't shown that one. So it forms a two intermediate. So you can see this is the intermediate one and this is intermediate two in this case. So now radical is on the nitrogen. So this radical on the nitrogen is the same species as shown earlier. This is the intermediate one, and this is the another intermediate is going to form, which has the chloro substituent at the 5 number carbon atom. So this is how, and after in case of like the aqueous media at the time of workup, so what happens? So this will be a normal SN2 type of reaction or just a substitution reaction. It gives the formation of 5 member cyclic 5 member ring containing nitrogen. This nitrogen attacks on the this carbon center and if chlorine Cl minus get eliminated from the reaction, right? And it gives the formation of this product which has the retention in the stereochemistry. So the stereochemistry here is unaffected. So as it is, only thing at this chloro, this will be uh, nitrogen attacks on the carbon, this chloride get removed. So if you just, as I shown earlier, if you just analyze the startings and the reagent, so you can clearly see here there was this was the CN, this was the labile bond, and in this case this between the bond between nitrogen and the chloride, it forms a radical at the nitrogen center. Once this radical form, so this form radical and this hydrogen, it shows the 1,5 hydrogen atom transfer. It gives the intermediate, so which has the this the remaining structure will be as it is. So this COOAET, and this is the nitrogen. So now the hydrogen and radical is on this position. So once this form, so another molecule of the starting, it will be a propagation step. So catalytic amount of this radical is propagate throughout the starting. So you can see. So this was the starting which has the NCl bond again. So this NCl bond and this intermediate one that I have shown earlier, they react to give the chloride species. So this chloro is formed, and then again there is a nucleophilic substitution. It gives the again five-member ring. So if you just look at this one, so this was the wrong option obviously because there is no any kind of change they have shown in the starting and the product, right? So you can neglect the options. See, this is the obviously not option. So they have just shown this ester to acid conversion. Obviously, it is wrong. Then in this case, you can see they have converted ester to acid. This is also again wrong. Here you can see in the first and second A and B options. So in the B option, they have given the NCl. So that's again the incorrect option. The option A is the correct option here. So if you look at the superficially, the reaction mechanism was the only the radical formation on the nitrogen, then the proton abstraction from the 5 number carbon atom, and then further there is a propagation step that in the detail mechanism that I have shown here. So the propagation step. So you can directly go up to the final options here by neglecting the other options and just by superficial. But for your information, it is good to know the detailed synthetic mechanism. So the detailed mechanism is here as mentioned. So there is first step the protonation of the amine followed by the radical formation and then radical formation by the homolytic cleavage, right? And further, once this radical is formed, so this intermediate it forms a intermediate. It abstracts the proton, that is the 1,5 proton transfer. So the radical form on the now on the carbon, and this again react with the one of the starting, so which has the NCl bond. So again, it induce the formation of this nitrogen radical and cleavage of this Cl. So this Cl now attached on uh, on the 5 number carbon where it was the radical. So yeah, this one. So and upon further nucleophilic addition of this nucleophilic attack of this amine on the carbon center which has the chloro group, it gives the formation of 5 member ring. So 5 member ring, and the obviously upon workup that the positive charge this proton is abstract by H water. So this water abstract this proton, it gives the minus H3O plus and gives the product. Any doubt in this question? Alright, if you don't have any doubt, I will move to the slowly to the next question, which is again based on the radical chemistry. So this question, it will major product form in the following reaction, and you have given the hydroxy, OBN, again the the 4 OBN groups and the one hydroxy group. They have again the specific stereochemistry, and in the reagent we have the N-iodosuccinamide. So this is the N-iodosuccinamide. I'll just pull up the detailed structure of this N-iodosuccinamide. I directly draw the structure instead of draw structure. I'll draw. So this is the structure of N-iodosuccinamide. This is nitrogen, and here is the iodine. So you can see. This is again kind of radical initiator, right? So it has the nitrogen and halogen atom, this hetero bond. So whenever you look such unusual bond, so obviously that's the active center. You should, I mean, primarily, you should have the idea. So that might be the active center, right? Yeah. Right. Up to here is okay. Now, once this starting react with the anidosuccinamide, what happens? So obviously, it forms a radical at the oxygen center, right? So here is the mechanism. So in this case, this is the hydroxy group. The radical form at this hydroxy group, and if I just draw the OBN means the CH2 pH group, right? pH. This is the again. So this is again O CH2 pH. Obviously, the same is O CH2 pH. I'll just draw in different manner so it will be easy for your understanding. OBN. So these all are the same, whether it is OCH2pH or, so these are the same, right? This is again, there was again one proton. Yep. Or you can write this OBN in this different manner. So all are same. OCH2. This is just a representation, different, right? Anyway, so once this OBN, this radical form at this oxygen, this radical, if you look at the, oh sorry, I just forgot to draw here oxygen atom. There was in between OBN, right? So this is O, then this is CH2, and then there is pH. So once this radical forms, so if you just label this one, so this one, two, three, four, and this oxygen, this proton is at the, oh sorry, this is the center, right? I just missed one place. This is one, this is two, three, four, and the five. Again, this is the 1,5 hydrogen atom transfer, right? And what happens? This proton is get abstract, goes to the hydroxy group, right? And the radical will be at that position. So this will be the intermediate step. So in which this is the pH, the radical now on this one, and again there was oxygen, CH2, and O. So the remaining group, OBN, all are same, all remain unreacted up to here. So this hydrogen uh, and this one, all right. So once this hydrogen atom uh, hydrogen is shifted to this oxygen, abstract the proton from or hydrogen transfer takes place. So this is what the radical will be on the this carbon, right, at this CH2 position. And once this form, again, as shown earlier, there was propagation step. So once this radical is formed, so what happens? So the some other, let's say, this NIS helps to cleave this bond, and this bond again the radical will be these two radical combine to form a newly bond between. So here was the radical, and these two helps to form a new bond. So it will give the formation of such five-membered ring, right? And there was hydrogen. That hydrogen was again taken by some other group. So it will be propagated. It will be propagated. So this hydrogen, this bond, what happens with this one? So this bond was broken homolytically. So only I have shown, you can see this half arrow. Half-headed arrow means hydrogen transfer of only one electron. Here also from this radical, obviously, it will be transfer one electron and it will help it forms a single bond. And the one remaining proton will be with the other one proton from this one will be with the it will help to continuously propagate the reaction, right? Whether it might be abstracted by these whether n iodosuccinamide or might or maybe other hydroxy group. So this hydroxy group can also uh, so this proton and this proton might be form some bond, or maybe the n iodosuccinamide, we have the n iodosuccinamide in the reaction. So this n iodosuccinamide also take this proton and it gives the formation of this 5-member ring. The remaining stereochemistry will be remains in the product. So this stereochemistry you can see will be as it is. There is no any change in the stereochemistry. So if you look at the options, so obviously this is not possible. So these other groups are not possible. Here again, hydroxyl group remain. That's again the wrong option. Right. So option A is correct option here. You can see uh, once this proton is formed. So if you just expand the structure of this OBN, you will understand. So there is CH2PH and there is one proton. So there is obviously 1,5 hydrogen atom transfer steps is involved. So radical formation at this position, 1,5 hydrogen transfer, and again the cyclization. So this sort of steps are involved. Similarly, here is again, you probably have already seen this such reaction many times. So you have given the ONO type of starting. So just full structure O. There is nitrogen and again there is again oxygen. So here there is a alkyl chain, right? So this ONO, what happens in terms of light? It forms a radical. So this radical formation step I can show. So the step, right. So this reaction is called as a Barton reaction. So you can see once this ONO that react with the radical, sorry, react with the light. So it forms a radical on the oxygen. And again, the similar manner, there is hydrogen atom transfer and the same steps involved. So there was hydrogen and this hydrogen got abstracted by the oxygen and radical got formed on this one. So this will be again OH because that radical is transferred and the remaining will be the same. And again, we have the ONO that the earlier this ON radical in the reaction mixture that radical and this radical combine to form a bond, right? So instead of drawing this much longer, I will draw it here, NO. So radical on the nitrogen. So this radical and this radical forms a bond. So it gives the OH, and this is again the same. So this is NO, not ON. N double bond O, right? And this remaining structure will be the same. And now what happen once this form? So this is the product from in this reaction. Further, it might be again the similar man as we seen earlier. This cyclization and all such steps. So this might be goes here, then ONO again get into that the other possibility. But we have up to we need to we have uh, up to here only, no further reactions. So in this case, you can see. So O and in this at the R solution, that's the wrong option. This again, sorry, not nearby position. That's obviously wrong. So you can see here 1, 2, 3, 4. Sorry, 1, 2, 3, 4, 5, So obviously at this 5 position only, the one radical, that because of the 1,5 hydrogen is most favored hydrogen atom transferred compared to the whether it is 1,3 or 1,2 or 1,4 or 1,6. This 1,5 hydrogen atom transferred is the most favored hydrogen atom transfer that you need to understand from this one. Because if you look at the structure, here is also hydrogen, here is also hydrogen, here is also hydrogen. So too many possibilities there are hydrogens, but only the hydrogen atom which is at the 1, 2, 3, 4 and the 5 number, that hydrogen only the preferred hydrogen. So that's why, because the if you look at the intermediate step, that is the uh, 6-member transition. So this hydrogen, you can see this intermediate step, you can see how close they can come. But if you have the hydrogen from here, either from here or from here, if you draw any way, any manner, that will not be such close to form a bond. So that's why this one 5 hydrogen atom transfer is most favored hydrogen atom transfer. Any doubt here? All right. Here, next question is again the same manner that we have seen earlier. Only here there is slight difference. You need to uh, assign exact stereochemistry in this product. So you can see we have also seen this earlier. This Bu3SNH and this bromo type of reaction. So what happens after this reaction and in presence of AIBN? So I will roughly show you what happens when this reagent react. So earlier we have seen one example with the such bromo, and there is again some other groups and all. But once this group react with the this Bu3SNH and in principle it forms a radical. So this bond cleaves homolytically, right? And it gives the radical at this position. But in this case, slightly there is difference. So what is the difference? So in this case, when this Bu3SNH react, so this bromo is now here. So the homolytic cleavage of this bond takes place. It gives a radical here. So this radical is now whether it is 5 exoteric mechanism or 5 endo. So you can see, sorry, 1, 2, 3, 4, 5. Right, the 5 exoteric mechanism takes place here. So this is how it forms a bond. So I'll just draw it, this one, and one electron from this one to form a bond, and it gives the radical or the methyl position. And this methyl position further again abstracting the proton from the solvent, it gives the this product. Now the question about the stereochemistry. So if you look at the cyclic transition state, so we have the two different options, whether it forms the chair-like transition state or the boat-like transition state. So these are the two transition states possible. But however, the boat-like transition state is less favored one because obviously we know the chair was most stable conformation of the cyclohexane. So in this case, you can see this radical forms at this position, so which is addition to the methyl substitution, right? So this radical and this, so there is a 5 exoteric mechanism, right? Right. So this 5 member ring form between this one, and in this case, this methyl directing downward and this methyl directing upward. So that's what you need to visualize in this one. The thing is how one can draw this chair-like conformation just by observing. So we have this radical. Now I need to convert. If someone asks how I can convert that one to the this type of system. So what you can do, just draw the radical at this position, and draw accordingly and consider this is one. So now obviously these are the two possibility, right? So among them, so this is the first draw one bond, then the remaining so this is the one up to here you can draw because so this one is the first, this is second. So I'll just give label parallelly. This second. Now you can see there is one methyl. So obviously one is here, one is here. This is the methyl, this is the hydrogen. Now you can, because I kept the methyl at the equatorial position because the when this bulky group at equatorial position it is a stable one. I can draw at the here also, but it will be less stable because the methyl at the axial position will be not a favored one. Then the remaining again here there is three. So this is the three. This is the four. At four also there is nothing. Then this is five. At five, yes, there is a double one. So here there is a option of double one, and you can see uh, the attachment also I have drawn as it is. This is hydrogen, the remaining as it is, remaining hydrogens and all. Now the bond between one and this five carbon is going to take place. So once this bond is formed, so you can see this methyl is directing upward and this methyl is directing downward. So if someone asks, show me how if I draw this methyl at the equatorial one, sorry, the axial one. So in that case, what happens? So this is the radical at which the ortho position there is a methyl. Now you can draw, if you just draw the remaining other remaining the groups. So these are the remaining groups, and now you can see if I forms a bond between this one, but this bulky methyl group at axial position less favored, right? Because of this, this group is less favored. This at the axial position and this transition state is less stable compared to the earlier one, this one. So that's why the methyl will be at the equatorial position here and directing upward. That's what I have drawn here. So if I just take the similar question, only change the substituent. So we'll see whether we are able to get the stereochemistry for that or not. So let's say we have some sort of such starting material, and particularly on which here there is the radical will be at, I'll just take the structure, right? That was the heter atom, right? Right. So up to here, and we have here instead of methyl, there is again the methyl and there is a third butyl group, right? And here the heter atom Br. So in that case, and here there is again some other functional groups, right? So in this case, what happens? So what is the stereochemistry form? So first step is the formation of radical, and this is the radical is gonna form. And once this radical is formed, so there is a transition state. So I will just draw the basic skeleton, and then I will draw the this is the basic skeleton, right? And here there is radical. Now the substituent. This substituent at the, now here the question whether here tert-butyl and here methyl or the vice versa, right? So the question about the tert-butyl and methyl groups. So in this case, you need to draw the tert-butyl again here at the equatorial position because not the methyl, because third butyl at the methyl only is the stable one. Otherwise, if you draw at the axial, there will be a lot of steric crowding, one because 1,3 axial interaction and all. So that's not feasible. So that's why here what happens. So this bond and this one bond, it helps to form the bond. And now in this case, so this is the radical will be at here, right? This bond is now cleaved, right? And here there was upward directing terbutyl group, downward directing methyl group, and this is the new bond, right? So I'll just draw new bond with the some other color. So this is the newly formed bond, right? And now if I just draw this structure in the 2D manner, so this is the third butyl group, this is the methyl group, and at this position, there will be again a downward directing this isopropyl group, right? So this way. So this is how the stereochemistry in this case looks like. So this all the stereochemistry depends upon this transition state. So whichever group, bulky group, that you need to keep at the uh, equatorial position, and the less bulky group at the axial position. So any doubt in this type of questions? If you have any doubt, please let me know so we can discuss that one. Otherwise, there is again the same question here. Here is slightly there is difference compared to the earlier few questions we have seen based on the this teen third butyl complex. Here there is a Bu3SNH. Earlier it was Bu3SNCl. So what happens when this Bu3SNH react with this compound which has the methoxy and the bromo at the ortho position? Sorry, not ortho, at the uh, adjacent position to each other, right? So in this case, what happens? So the first step was the initiation. So it will be a stepwise manner, just mechanism I have shown. So in this case, this is the most labile bond in this molecule, and this breaks to form the HX and the tin radical. And this tin radical obviously it will react with this bromo. So this bond it homolytically get close and it forms a radical at the adjacent position to the methoxy. Now we have this again the Bu3SNH because the Bu3SNH is there in the reaction mixture. So again the second homolytic cleavage takes place. It forms the hydrogen transfer takes place on that carbon. So or to which this radical. So this is the newly formed radical with these some newly formed bonds, which is comes from the hydrogen come from the Bu3SNH, and we get the product. So this is the very simple reaction. So in which it will only the first there is a bromo and the carbon bond homolytic cleavage takes place. It forms a HBr, right? And so this HX is the HBr. And now the second again, the second molecule, the radical form on the carbon, which is again react with the second molecule of Bu3SNH. So it gives the hydrogen attached on this radical. So this is basically we can convert the bromo, the any halo compound to the corresponding uh, instead of CX bond, we can convert it to the CH bond. So this was the sum of the reaction based on this radical chemistry. There are again some other reaction that I have added into the these slides. So we can move to the that one also. But before going to discuss these questions, so I would like to take any questions or doubt from the audience. So do you guys have any doubt regarding the content that we are seeing here? All right. So the next question here is again the photochemical reaction. So we have the systems. You can see there are two isolated olefins, and when it react with the light, what happens? So just for understanding, simple understanding, I just rewrite these the structures of this olefin. So these are the methyl groups, right? And the remaining part, that's the one phenyl, the other phenyl, and here which has the methyl, and again one methyl. So what happens when this react with each other? So there will be a first step, first reaction will be on this, the radical rearrangement. The so here you can see as I have shown earlier. So there will be a radical formation. So if I just draw in the same, so how the radical is gonna form? So here there is one radical, here there is another radicals. The remaining group will be as it is. So this is pH and this is methyl methyl. These are the radicals. And what happens? The bond rearrangement takes place. So right. So when moving from this to this, the newly bond formed bonds will be, this bond is going to form from here, right? So so there is a new bond formation. So there is the steps. Finish. This is the newly bond, and the radical will be here and here. Right. So this and the remaining group will be the same. That will be unupdated. The pH, pH. This is methyl. This is methyl. And then again, so this radical is stable one. What happens? This bond cleaves homolytically in this manner. I will draw with the some different color. pH, pH, and methyl methyl. So there was the radical, and this is the radical. Now, among these two radicals, so which radical is stable one? Obviously, the radical which is adjacent to the phenyl ring, because it gets stabilization by the resonance effect of this phenyl. So now, this bond get cleaves and it forms a double bond. So this will be remain. It forms a double bond. Now there was like this manner. There was a methyl, and the radical is now on this position. So the remaining this bond phenyl phenyl will be the same, and here again one another radical will be as it is. And further, next step is the again the cyclation of these two radical forms cyclize to forms a bond. So I just rewrite this structure. So this is the structure, right? To which this is the phenyl, this is the phenyl, and this is again the phenyl, and there was a radical, and this is I just draw in this manner. This is the radical another. These two radicals combines to forms. It gives the formation of the new product. So which is the this is the this part. This is the another part of molecule which has the phenyl and the phenyl. And now this was the methyl methyl, and this is the again newly formed bond, right? So this is how the it forms a this is the newly formed bond. So this is the product in the following reaction. So this was the starting material in presence of light. So it forms such radicals, and obviously they are not tetra radical is not like that. They will be concentrated in the concentrated manner, concentrated reaction mechanism. So the bond formation, bond breaking takes place simultaneously. So that sort of. So you can see here there is a mechanism, but it's the same mechanism that I have shown. So this is the starting material, the first step. This is the second step, and this is the third step. This is the fourth step, and this is the fifth step. Here is again the same reaction. There is slightly, we have the keto in the starting material, and there is a two center, which is chiral center. In presence of light, what happens to this molecule? So if you just draw the structure, elaborate the structure, instead of elaborating, this is the same structure. I can just expand. Right. So this is the structure, and you can see there is a influence of light. So this bond get closed, right? The first step was the influence of Vishnu. There is here radical and here radical formation. Then first I will show roughly, and then we'll see the stepwise. So in this step, what happens? So there is a radical at the oxygen center and the carbon center in terms of light. Now this bond cleavage, homolytic bond cleavage takes place. It forms a bond and forms a radical. So I'll just draw. This is OH. The radical will be at this position. Now this stereochemistry will be remain as it is. Here there will be a methyl and there's another methyl. Right. Now radical will be at this position and radical is now on this position. And once this radical form, so you can see this is the homolytic bond cleavage takes place again. So it gives the this OH as it is. So there is a bond, so double bond formation. I just draw the some different color. So this is OH will be remain as it is. This ethyl, this is ethyl again same. So this is how it formed. It is then converted into the obviously keto-inert automerization, right? And this is the product. So this is the one product, and the remaining half part. So this was the half part. So which is again methyl. This is again methyl, and there is again the hydrogen and the methyl. So yeah. So these are the two products. So this methyl. So bond cleavage takes place in this one. Here there is no any stereochemistry in the final product involved. So that's okay. But yeah, so this is the enol and this is the methyl product. This is the product form. But if you look at this enol, which is then obviously then converted into the keto. So someone can also might expect in the option. So this might be the this both are equivalent. So what's the difference in this one? No, this is they have cleaved from wrong side. In this case, they have cyclized. In this case, again they have cleaved from wrong side. Like so, option A is the correct option here. And if you look at if you want some detailed mechanism for also, so here is the mechanism. It is also the same that I have shown. So once it forms a radical. So here radical. Then again the uh, hydrogen transfer and the radical on the carbonyl center here. So this radical, what happens? So this radical goes here. The one radical comes to here. Yeah. So it goes here. One from this bond, then one from this bond, and one from here. So basically, this bond is get cleaved at the end of this reaction. So and these are the product. So it is just I have shown the ketone or topmerized product. But if you look at the uh, here. So this one can also be at the end will convert into the this one. So there is a kind of indistinguishable. So I'm not sure uh, whether we can select this one also, because this and this will be the same, which is again this one. So this product, let's say product X, this again the same X. So it is indistinguishable. Anyway, but as of now, it's good. You can select this option, option A. All right, the next question is again the same mechanism, ONO. It forms a radical. So I just draw in the superficially. So here there is a O radical, and there is again NO radical. And again at the 5 number position. So this is the proton at the 5 number position. So one, two, three, four, and sorry, this is one, this is two, three, four, and five, right? Or there might be a proton from here. There is one more methyl here, right? Or here this side also one, two, three, four, and this is five. That is on the axial methyl group. So obviously, which one is the most preferred or most near to the this oxygen radical? So obviously, the proton which is at the so this was O, and this is there was the methyl group, right? So here is one proton. There is again one CH3 group. Here there was CH3 group, because these protons are not nearby or accessible to this O radical. So that's why this O radical attract this proton. So obviously there is a radical here, and the remaining structure will be the same. So that's just a similar mechanism in which you can see this O will be the abstract the proton from this accessible proton. So this accessible proton is abstract by the O radical, and it forms a radical in this position, right? And next, what happens? So once this proton is formed, there is in our reaction mixture there is the NO radical, and this NO radical is then uh, gets attached at this position. So it will be in this way. So this is OH, and here there will be CH2 NO. All right. So in this question, so this is the wrong option. Again, this is again wrong because they have added somewhere else. So this is the option D is the correct option here. Not this one also. Why not this one? Because this is equatorial position, and which is to access this proton, it is difficult. So here, so there is proton. So one, two, three, four, five. Okay, but this proton is not accessible because this is directing downward, and this ONO directing upward. So in this way, you can, in some competitive exam like NET, GATE, or any kind of other bar examination, if such question comes, you can clearly just eliminate the options which are not feasible just by by seeing the options. So in this also, so this reaction doesn't stop at this position. If there is absence of these such accessible protons, in that case it might be the product. But in this case, there are such accessible protons. So these protons. So that's why reaction goes to completion to the and we get this option D as a product. So you can see this reaction mechanism. So this is the mechanism that again the same reaction mechanism. All right. So the next question here is the now we have slowly moved to the some different type of questions. So they are not particularly based on the particular radicals. It is, but not that type of that we are seeing the Barton reaction or oxidipy or dipy or type of reaction. So if you look at the starting material in this question, we have given a starting and then the third butyl. So this third butyl will be in this manner. C double bond O H. This is the third butyl acid, right? And we have given the NH4 twice Es2O8, AgNO3, H2SO4, water at 70 degrees Celsius. So this is basically the mini-side type of reaction. So in this case, the product will be the third butyl substitution at the ortho to the this heteroatom nitrogen atom. So this is the product form after the completion of this reaction. So if you just look at the reaction mechanism of this reaction, so what happens uh, because of this third butyl group? So the radical initiation. So this is one influence of this SO42 minus. It goes converted to the S2O8 2 minus, and this Ag 2 plus and the Ag plus. So this Ag plus converted to Ag2 plus, again Ag2 plus converted to Ag plus by just giving the radical to the. So basically what happens, this radical is formed double bond O radical. So this is the course of reaction. So it is a cyclic process. Cycle. This is the this Ag2 plus get converted by Ag2 plus get converted by to the Ag plus by reacting with this terbutyl acid, and it forms a radical at this O. Once this radical is formed, so this can undergo minus CO2 takes place. So the CO2 get evolved and it forms a terbutyl radical. This radical is now when react with the such aromatic system. So in this case, I'll just redraw the positioning of these bonds. So when it react with this starting material, it gives the radical will be formed at this position and radical will be on the nitrogen. So in this case, the radical will be on nitrogen because this bond is involved in the bond formation, and the radical on the nitrogen is stable compared to the radical on the terbutyl. So the reactivity drives to the formation of this product. Right. So this product form, and the last step will be it takes the again the second cycle of Ag 2 plus 2 Ag. This is the product. So the product in the options that earlier given, so the product will be on the this one. So this is the product form. So these are the wrong options. So in this case, whatever the acid, tert-butyl acid, whether it is tert-butyl acid or any substitution substituted acid, so it might be any substituent or any simple R, they have given the acid and OH. So in that case, this R radical is formed in by the combination of reagent. And once this radical form, so it goes attack to the position, ortho position to the such pyridine ring. So that you need to keep in mind. All right, any doubt up to here? Or I have some more two, three questions. So which is basically based on the burst type of reaction. So in this case, I will just show this question. So in this particular question, the predict major product formed in the following reaction, and you have given this methyl, and there is a triple bond for the methyl, and given the sodium in the NH3. Right. So what happens? This sodium and NH3, what happens? It forms a Na and this NH3. So this salt, this forms the such electroid salt, and the radicals, it gives the radical to one electron to the system. So what happens? So this methyl, this bond get close on forms bond, and there is one methyl, and it gives the electron to this one, and it forms a negative charge. Once this form negative charge, it abstracts the proton. So from this NH3 and use the formation of the product, sorry, the formation of intermediate step. So I will just draw this in the big manner. Right, up to here, we have came up to here, right? So we have this one, then we have R2. So once the NaNH3, this salt give the electron, this entire salt transfer electrons to the system. So it abstract the proton. There will be negative charge, and this will be from trans to get the stability. So here R, it absorbs the proton, okay, R2. And again, the second molecule, so there was a one radical, right? So once this proton gives here one electron, it should be shown in half-headed arrow. This one electron goes to this position, so the negative charge goes to here. So once this negative charge goes here, there is one radical. So another NaNH3, this entire electrolyte salt gives another electrons. So it again forms a negative charge here, R here, and again taking proton from the solvent, it gives the formation of this. So these are the first proton, this is the second proton in this manner. So the steps, this one, this transition step, it is in the transform. So this transition state gives the trans product. Because of the steric repulsion on the scene, if you draw the scene, so what will it will be? It will be negative charge here and radical here. So that's doesn't prefer. There will be a steric repulsion, right? That's why this cis, sorry, this trans is more preferred. So what if you want a cis transition, a cis product? So what, at that time, what kind of reaction you perform? So R triple bond R and Na NH3 NH3 the THF minus 17 degrees Celsius. So it gives the R, it gives the trans, right? What if you want a cis product? Then in that case, what kind of reagent combination you can use? So have you heard about the Lindlar catalyst? So that catalyst we generally used for the cis transition. If you want cis, if you want a cis olefin from the alkene, so it goes via some different mechanism. So in that case, what is the reagent formation? This is the R1 and this is the R2. So this is a question for you. So what are the reagent condition? So you should find the answer for this one. All right. So I will stop here for today. So if you have any question, please let me know. I will wait for you for 5 10 minutes and then I will stop here. All right.